When a machine breaks down, a technician has to come in and fix it. The faster they can fix the machine, the faster the factory can go back to producing product and making profit. But machine manuals can be thousands of pages long, and a fix can involve several manuals. Could an LLM help the technician find the relevant information faster, fixing the machine faster? The right information might not be on one page, or it might be in a table or a diagram, so simple Control F won't work. We were previously working on a RAG pipeline to solve this, then Google came out with long context. Can we use this to simplify our codebase while still being performant? We demo this with the Volkswagen Vanagon official factory repair manual. I own a Vanagon and tried out Vanlife. It involves a lot of breakdowns and fixes. A lot of people out there could be helped by a faster way to troubleshoot, so this seems like a good demonstration. It's relatable to people and still relevant to fixing machine breakdowns using thick manuals. That's enough context. Let's try out the tool. Now we're in the notebook's example queries. There are 4 queries. Each shows how the tool performs on a different query type that the user might have. The first is a general search. The user wants to know where information is. The output includes a direct answer to the question, then displays the relevant pages. This is important because the user wants to look through the information themselves, and displaying the pages also gives them the confidence that the right pages have been found. In the second example, a user is looking for a specific type of information, a procedure. The output includes the steps of the procedure, or it may just point to the pages that procedure is on. This time, the importance of displaying the relevant pages is to give the user confidence that the steps are accurate. This example shows the benefit of long context by including the procedures for different engine types, which were in different parts of the manual. In the third example, a user is again looking for a specific type of information, this time an exploded schematic. Because the sought-after information is visual, the output text is less important than the displayed page. The last example is searching for a detail, whether it comes from text, an image, or a table. The output text is the answer. And again, displaying the page gives the user the means to check that answer is accurate. So that's what the tool can do so far. How does it do that? Let's walk through the notebook from the top. So now we're at the top of the notebook. Let's go through the code. The first parts are necessary, but a bit dry. Make sure to stick around for a discussion of advanced prompting techniques. First, we run our installations and imports, and configure the API. Then we convert the PDF to images, and upload those to the Gemini AI platform using the Files API, saving the file names. Next, we add the page number as a string before and after each file, so the model knows what page number each image has. This is something we had to do because the page numbers in the manual are particularly convoluted. This next step is really important to reduce latency and save costs. This is where we cache those files and initiated the model from that cached content. The code is simple, where you pick your model, write the system prompt, include the context in the content argument, and set how long you want the cache to last for. Then create an instance of the model using the fromCached_content method. With this setup done, we draft our main prompt as a function, which first takes in the user's query. We then use 4 techniques and communicate each one of those as a step to the model. The first is page scan, where we combine chain of thought with asking the model to go through the entire document. This helped the model go through the whole document rather than stopping early when it thought it found an answer. The second is extracting page content. By having the model recreate the content, it was able to be more accurate on details than reading those details directly from the document. The third technique is error correction, where we give the model space to check its work and redo prior steps if it finds a mistake. Since models are probabilistic, they can make mistakes, and this allows it to course correct. The fourth is giving the final answer in XML tags. Tags make it easy to extract the information compared to keywords or whitespace. We considered using structured outputs, but found tags were good enough. To reinforce these techniques, we use few-shot prompting, or in other words, we give the model multiple output examples. This technique helps the model stick to the instructions and the format we gave it. With our main prompt written, we need to add 3 utilities for the tool. The first is extract answer and references, which takes the model response and extracts the answer and page numbers from the XML tags. The second utility is display selected pages, which takes a set of PDF images and the indices of the pages that we want to display, and displays them in a grid. If indices are invalid, it skips them and communicates this. The last utility ties everything together. Get answer from manual takes the user query, the context-laden model, and the PDF pages. It adds the user's query to the main prompt, calls the generation API, then uses the first 2 utility functions to extract the information and display the answer and relevant pages. And that's how it works. If you want to check it out yourself, we included a basic user interface block where you can change the query. Just note that you'll have to generate your own API key and add it as a secret. Otherwise, you can look at the pre-run example queries below the UI block that we walked through earlier. And that's the project. Thanks to Fluxworks for letting us visit your factory.